It's now time to check out Newton's third law. Just a quick recap of our other two laws we've already discussed. Law 1 is all about inertia. Object in motion stays in motion because of its mass. It resists to have any change until that unbalanced force comes in. Law 2 has to do with acceleration being able to be calculated knowing an object's force and mass. We can do a lot of calculating back and forth with those variables. And finally then, our third law is known as the action-reaction law. So law number 3 is action-reaction. So as always, we start out with a couple key ideas. We want to think about how these forces do not cancel each other out, which seems a little bit backwards than what we've been talking about so far. We also want to know why would objects accelerate differently based on their action-reaction forces, and of course we want to be able to give some examples as those action-reaction forces occur around us in our everyday life. So here we go. This third law states that for every action that occurs, there is an opposite and equal reaction. So for every action force, if you will, for every action force that occurs, there's an opposite and equal reaction force. And so these nicely named action-reaction forces occur in pairs. It means they happen together. One does not happen without the other. So they go together with an action. So let's look at this example. Over here on the right-hand side, we're going to practice writing out action and reaction forces. So notice over there it says example number 1, action, reaction. Here's our first event, is someone heading a soccer ball. So when we write these reaction forces, our key word here is going to be push or pull. We got to think about these being a force. So those are pretty important force terms. So we got to think about what are the two objects interacting, and then how are they interacting. So here with the heading a soccer ball example, we of course have the head and we have the soccer ball. So those are going to be my two key objects. What's happening between them in this example is a push. So the action force could be the head pushing on the ball. So I would write down head pushes ball. That's my action. At the exact same moment, because these happen in pairs, there is an equal, and you can see by the size I drew my arrow here, there is an equal and then opposites going the other direction, reaction force happening at the same time. So as the action is head pushes ball, the reaction is simply the reverse of that. Ball pushes head. So again, I figured out my two objects, the head and the ball, and the force between them this time is a push. So as the head pushes on the ball at the same time puts an equal and opposite force on the head. So my action is simply head pushes ball, reaction is the opposite, ball pushes head. Now it's important to note that the action force does not cause the reaction force. Okay, it's not that the head pushed the ball and then a couple seconds later the ball pushed back. It's that they happen at the exact same time. So the action force does not cause the reaction force. They happen at the exact same time. So again, on the right-hand side, you've got an example of a guy jumping here on the trampoline. Think about, again, the action-reaction forces. What are the two objects involved? Here we have the guy and the trampoline. And what's going to be a better description? A push or a pull? That's what we want to figure out. So for this example, my action could be the guy pushes the trampoline, and my reaction would be trampoline pushes guy. Again, the phrase is just flipped around. Sometimes I have people say guy jumps on trampoline, but when we flip it around, it doesn't make sense that the trampoline is jumping on the guy, right? When we think about it, we are putting a downward force on the trampoline, and at the exact same time, the trampoline is putting an upward force on us. Again, happening at the exact same time. So if you haven't yet recorded your action-reaction forces for the trampoline and the guy, go ahead and do that on the right using that basic term, push between the two objects. But I have another question for you over there on the right-hand side. What are we noticing about the acceleration of both of those objects? What is noticed about the acceleration of the guy compared to the acceleration of the trampoline? So go ahead and pause and make a little note. What is noticed about their acceleration? Hopefully you thought about it and recognized that those objects have different accelerations, and that difference is based on their mass, right? If we think about our formula from law number 2, the force being exerted on each object is the same, but the masses of the objects are different, causing a different acceleration. So go ahead and circle up over there. If the object has more mass, what will we see about its acceleration compared to the object that has less mass? So the more mass is obviously the trampoline, where the less massive object is the man. So what is noticed about each one's acceleration? So as we practice these action-reaction forces, we'll see quite consistently that acceleration is different between the two objects, even though the forces on them are the same. Now, as we think about these action-reaction forces, we have a tendency to think about them canceling out and becoming balanced, but they actually will not cancel out. Action-reaction forces don't cancel, and that's because they're happening on different objects. When we did our free body diagrams before, and we talked about balance forces, they were happening on the same object. However, the action-reaction forces are happening on different objects, so it's not possible for them to cancel out. Here's another example for you to think about. Action-reaction within this entire image. Make sure as you're writing your action-reaction forces that you're using that keyword, push or pull, and you're thinking about two objects that are in contact with each other. So the two objects have to be touching. So I can't officially say that the elephant is pulling the tractor. I have to think about, well, what are the two objects touching in this situation? So go ahead and pause and work in your action-reaction forces. So again, while these action-reaction forces are equal and opposite, they will never balance or cancel each other out because they're happening to different objects. So a few more action-reaction to practice over there on the right. This is going to be for example number 3 there on the right. Thinking about action-reaction, again, think about what two objects are involved. And what would the force be like? Is it a push or a pull? And when you write the action-reaction, make sure they're opposites of each other. And it really doesn't matter which one comes first. They can alternate. Final example here, number 4. Thinking about two objects. This picture has a few different options, right? You could use the guy and the boards, or you could talk about the guy and the ice underneath. So as you write your action reaction, make sure again we're using that keyword between those two objects. And again, kind of take it one more step. What would I notice about the acceleration? So final thoughts here in your summary is to answer, why are these forces not canceling out? Why do the objects have different accelerations? And then see if you can give an example of an action reaction in your everyday life.